Ask anyone what electricity is and they'll say electrons flowing through wires. Ask them why batteries die. They'll say the electrons run out. Ask them what AC and DC mean. They'll give you textbook definitions that explain nothing. Richard Feynman once said that nobody really understands electricity, and he was right, but not for the reasons you think. Come in, sit down. We need to talk about something you use every single day, but probably don't understand at all: electricity. Now, before you get defensive, let me tell you a story. In the 1960s, Richard Feynman was asked to serve on a curriculum committee for California schools. They wanted him to review science textbooks, approve them for use in classrooms. He read through them, and he was horrified. Not because they had wrong facts. The facts were mostly correct, but because they explained nothing. They gave students words without understanding. They made kids memorize definitions without ever showing them what was really happening. One textbook said, "Energy makes things go." Feynman asked, "What does that mean? What is energy? How does it make things go?" The book never explained. It just repeated in different words, energy is the ability to do work, and work is when energy is transferred. Circular, meaningless. This is how most people understand electricity. They know the words: current, voltage, resistance, Ohm's law. They can plug numbers into formulas, but they don't actually understand what's happening. So let me tell you what everyone gets wrong. Not just one thing, multiple things. A whole collection of misconceptions that textbooks either teach directly or allow to persist through vague language. And then I'll show you what Feynman would show you, the real picture. What's actually happening when you flip a light switch, charge your phone, or get shocked touching a doorknob. Here's the first thing everyone gets wrong. Batteries don't store electrons. You probably think a battery is like a tank full of electrons. You use them up, the battery dies, you throw it away or recharge it to refill the electrons. Wrong, completely wrong. A battery doesn't store electrons, it stores chemical energy. And it uses that chemical energy to push electrons that are already in the wire. Think about it. You have a wire. That wire is made of copper. Copper is a metal. Metals have free electrons throughout their structure. Trillions upon trillions of electrons already there, ready to move. The battery doesn't provide those electrons. The battery provides the push. It creates an electric field that makes those electrons drift in a particular direction. How? Through chemistry. Inside the battery, chemical reactions create a separation of charge. One terminal becomes negatively charged, excess electrons. The other becomes positively charged, deficit of electrons. This charge separation creates an electric field. When you connect a wire between the terminals, that electric field pushes electrons through the wire. The electrons were already in the wire. The battery just pushes them. And when the battery dies, it hasn't run out of electrons. It's run out of chemicals that can create the charge separation. The chemical reactions have gone to completion. There's no more energy available to maintain the electric field. You can recharge the battery by forcing the chemical reactions to run backward, restoring the original chemical configuration. You're not adding electrons. You're restoring the chemical energy. This is fundamental, and most people never understand it. Here's another one. You're taught that current flows from positive to negative, and you're also taught that electrons flow from negative to positive. And somehow you're supposed to hold both of these contradictory facts in your head simultaneously. Let me clear this up. Electrons, which are negatively charged, flow from the negative terminal to the positive terminal. That's the actual physical motion of actual physical particles. But we define current as flowing from positive to negative. Why? Because of a historical accident. Benjamin Franklin in the 1700s decided that there were two types of electricity, positive and negative. He had to choose which was which. He made a guess. He said that current flows from positive to negative. He guessed wrong, or rather, he didn't know about electrons yet. Nobody did. Electrons weren't discovered until 1897. By the time we discovered electrons and realized they were negatively charged and that they moved from negative to positive, we'd already built an entire electrical engineering convention around Franklin's definition. Changing it would mean rewriting every textbook, every schematic, every technical document. So we kept the convention. We define current as the flow of positive charge from positive to negative, even though what's actually moving is negative charge from negative to positive. This is called conventional current, and it works fine for calculations. Direction-wise, a flow of negative charge to the right is equivalent to a flow of positive charge to the left. The math works out the same. But it confuses students because they're told electrons go one way and current goes the other way, and nobody explains that this is just a convention. It's arbitrary. We could have defined it the other way. Feynman hated this. He'd tell students, forget about conventional current. Think about what's physically moving, electrons, from negative to positive. That's what actually happens. People talk about voltage like it's the strength of electricity. High voltage is dangerous. Low voltage is safe. More voltage means more power. This is confused thinking. Voltage isn't strength. Voltage is potential difference. It's the amount of energy per unit charge available to push charges through a circuit. Think of it like height. If you have a ball on a hill, the height of the hill determines how much potential energy the ball has. The higher the hill, the more energy it can release as it rolls down. Voltage is like that height. It's a measure of energy per charge. High voltage means a lot of energy per electron. Low voltage means less energy per electron. But here's the critical part. Voltage alone doesn't tell you how much total energy is involved. That depends on how much charge is moving, on the current. A static shock from touching a doorknob can be 10,000 volts or more, but it doesn't kill you. Why? Because the total amount of charge involved is tiny. High voltage but infinitesimal current. Very little total energy. A car battery is 12 volts. Very low voltage, but it can deliver hundreds of amps of current. Low voltage but huge current. Enormous total power. That's why you can touch both terminals of a 9-volt battery with your tongue and just feel a tingle. The voltage is low. The resistance of your tongue is relatively high, so the current that flows is tiny. But if you stuck a fork into a wall outlet, don't do this, you'd get 120 volts at potentially several amps. That's enough to kill you, not because of the voltage alone, because of the combination of voltage and current. Power, the rate of energy delivery, is voltage times current. Both matter. This is what Feynman would emphasize. Don't think of voltage as how strong the electricity is. Think of it as how much energy each electron carries, and then think about how many electrons are flowing to determine the total power. I mentioned this earlier, but it's worth diving deeper, because this misconception leads to so much confusion. Electrons in a wire move incredibly slowly, about 1 millimeter per second in a typical copper wire carrying a typical current. That's not a typo. 1 millimeter per second. You could watch an electron drift through a wire and you'd fall asleep from boredom. But wait, you say, when I flip a light switch, the light comes on instantly. If electrons move that slowly, shouldn't there be a delay? This is where most explanations fail. They tell you the wire is full of electrons, so when you push one in at one end, one pops out at the other end immediately, like a pipe full of water. That's closer to the truth, but it still misses something important. What's actually propagating at nearly the speed of light isn't the electrons themselves, it's the electromagnetic field. When you close a switch, you establish an electric field throughout the circuit almost instantaneously at the speed of light through the medium. That field exists everywhere in the circuit at once, and it pushes on all the free electrons in the wire simultaneously. So all the electrons start drifting at the same time. The ones near the light bulb start drifting immediately, not after waiting for electrons from the battery to arrive. The electromagnetic signal travels fast. The electrons drift slow. The light comes on quickly because the field reaches the bulb quickly, not because electrons race through the wire. This is crucial for understanding anything involving high-frequency AC, radio, transmission lines, or any practical electrical engineering. The electrons aren't really going anywhere. The field is doing all the work. Alternating current, AC. Everyone knows that in AC, the current alternates direction. It goes forward, then backward, then forward, then backward. 60 times per second in the US, 50 times per second in most other countries. And people imagine electrons flowing one direction, then reversing and flowing the other direction, back and forth, 60 times per second. That's not wrong. That is what happens. But here's what people don't understand. The electrons barely move at all. Remember, drift velocity is about 1 millimeter per second. In AC, the electrons oscillate 60 times per second. So how far does an electron move in one cycle? 1 millimeter per second divided by 60 cycles per second. That's about 0.07 millimeters per cycle. The electrons are wiggling back and forth by less than the thickness of a sheet of paper. They're not traveling. They're vibrating, jiggling, oscillating in place. So how does AC power work? How does energy get from the power plant to your house if the electrons aren't actually traveling? The electromagnetic field. Again, the field oscillates. The field carries energy. The field propagates at nearly the speed of light through the power lines. The electrons just wiggle in place in response to the field. This is why AC is so useful for power transmission. You can change the voltage easily with transformers. You can transmit power over long distances efficiently. Not because electrons are flowing great distances, but because the electromagnetic field is doing the work. And this is why frequency matters. 60 hertz means the field oscillates 60 times per second. Higher frequencies have different properties. Radio uses much higher frequencies, millions or billions of cycles per second. The electrons still just wiggle, but the field carries information, energy, at those high frequencies. Resistance. Everyone's taught that resistance is like friction. Electrons bumping into atoms, slowing down, getting stuck, converting their kinetic energy into heat. This metaphor is terrible. It's misleading. It gives you completely the wrong picture. First, electrons aren't slowing down in a resistor. Their drift velocity is determined by the electric field and the properties of the material. In a high-resistance material, the drift velocity might be slower, but that's not because electrons are getting stuck. It's because the material's structure makes it harder for electrons to drift. Second, the energy that becomes heat isn't the kinetic energy of the electrons. Electrons are moving at about 1 millimeter per second. The kinetic energy associated with that drift is absolutely tiny, nowhere near enough to account for the heat generated by a resistor. So where does the heat come from? The electromagnetic field. The field is carrying energy. The resistor extracts energy from the field and converts it to heat. How? Through collisions? Yes, but not the way you think. Electrons in the material are constantly colliding with atoms. These collisions transfer energy from the ordered drift motion into random thermal motion. But the energy being transferred isn't the drift kinetic energy. It's energy from the electric field. Think of it this way. The electric field does work on the electrons, giving them energy. The electrons collide with atoms, transferring that energy into heat. The field continuously supplies energy. The collisions continuously dissipate it as heat. The resistance of a material is a measure of how efficiently it converts electromagnetic field energy into thermal energy. High resistance means efficient conversion. Low resistance means inefficient conversion. This is why superconductors have zero resistance. In a superconductor, electrons don't collide with atoms in a way that transfers energy. They move through the material without dissipating energy. No collisions means no conversion of field energy to heat means zero resistance. Here's something that confuses people endlessly. Why do electrical circuits need two wires? Why do you need a complete circuit for electricity to flow? People think you need two wires because electrons flow out of one wire and back through the other, like water flowing through a pipe system. You need a complete loop. That's sort of right, but it misses the deeper truth. What you really need is a potential difference and a path for charge to move. Here's an example. Lightning. Lightning is a massive flow of electrical current, millions of amps, but there's no wire, there's no circuit. How does it work? There's a huge potential difference between the cloud and the ground, thousands or millions of volts. That potential difference creates a strong electric field. If the field gets strong enough, it ionizes the air, making it conductive. Current flows through the ionized air from the cloud to the ground. There's no return wire. The ground itself serves as the return path. Charge flows from the cloud to the ground through the lightning bolt and then spreads out through the ground, eventually making its way back to regions of opposite charge. Or consider static electricity. You shuffle across a carpet, building up charge on your body. You touch a doorknob, zap. Where's the complete circuit? There isn't one in the traditional sense. You're at a different potential than the doorknob. Charge flows briefly to equalize the potentials. That's it. The reason we use two wires in electrical systems is for control and efficiency. Two wires create a well-defined path for the current, making it predictable and manageable. One wire carries current out, the other carries it back. But fundamentally, all that matters is potential difference and conductivity. In some systems, you don't even need two wires. Single-wire earth return. SWI systems use one wire and the ground as the return path. Radio transmission uses antennas, one wire effectively, and the return path is through the electromagnetic field and ground. This is what Feynman would emphasize. Don't think of circuits as needing loops because electrons need a round-trip path. Think of them as needing a potential difference and a way for charge to flow. The two-wire setup is just the most practical way to achieve that in most cases. Grounding, the earth connection, the third prong on your plug. Everyone knows it's for safety, but most people have a completely wrong picture of what it does. People imagine that if there's a fault, excess electrons leak into the ground wire and get dumped into the earth, safely dissipating, like pouring water onto the ground where it just soaks in and disappears. That's not what happens. The ground isn't an infinite sink for electrons. Electrons aren't disappearing into the earth. Here's what grounding actually does. It establishes a reference potential, 0 volts. By convention, we call the potential of the earth 0. When you ground something, you're connecting it electrically to the earth, ensuring it's at the same potential as the earth, 0 volts. Why does this matter? Because potential differences cause current to flow. If a wire in your toaster shorts against the metal case, the case becomes live. It's at the same potential as the hot wire, maybe 120 volts. If the case is grounded, there's now a potential difference between the case trying to be at 120 volts because of the short, and the ground at 0 volts. Current flows through the ground wire, a lot of current, enough to trip a circuit breaker. The breaker trips, the circuit goes dead, you're safe. If the case isn't grounded and you touch it, you become the path to ground. The potential difference is between the case, 120 volts, and you touching the ground, 0 volts. Current flows through you. You get shocked, possibly killed. The ground wire isn't absorbing electricity. It's providing a low resistance path to 0 potential so that if there's a fault, current flows through the ground wire instead of through you. And the electrons that flow through the ground wire, they don't disappear. They flow through the wire, through the earth, and eventually back to the neutral wire at the power panel, completing the circuit. The earth is just part of the conductive path. This is what Feynman would make clear. Ground isn't a magical electron sink. It's a reference potential and a safety path. So what is electricity, really? If all these common explanations are wrong or incomplete, what's the true picture? Electricity is the organized motion of charge carriers, usually electrons, in response to an electromagnetic field. That field is created by a potential difference, usually maintained by a battery or generator. The field extends through space, carrying energy. The electrons respond to the field by drifting slowly, but the field propagates quickly. When you flip a light switch, you complete a circuit, allowing the electromagnetic field to establish itself throughout the system. That field pushes electrons everywhere in the circuit simultaneously. The electrons wiggle or drift slowly, but the field delivers energy to the load at nearly the speed of light. Resistance is a measure of how efficiently a material converts electromagnetic energy into heat. Voltage is energy per charge. Current is charge flow per time. Power is the product of voltage and current, the rate of energy delivery. AC is when the field oscillates, making electrons wiggle back and forth. DC is when the field is steady, making electrons drift consistently in one direction. Batteries don't store electrons. They store chemical energy that creates and maintains a potential difference. Ground isn't an electron sink. It's a reference potential and a safety path. The dangerous part of electricity isn't voltage alone or current alone, but the combination, the total power delivered to your body if you become part of the circuit. This is the real picture. Not water in pipes, not friction, not electrons racing through wires, but electromagnetic fields permeating space, pushing charges, delivering energy, following Maxwell's equations. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He was being honest about the limits of human understanding, even for experts, but he might have said the same thing about electricity. Not because electricity is as fundamentally mysterious as quantum mechanics, but because most people, even many physics students, carry around a collection of half-truths and misconceptions that they never question. They know the words. They can solve the problems, but they don't understand what's actually happening. And that bothered Feynman, because understanding is the point. Not memorization, not calculation, understanding. Being able to picture what's happening physically. Being able to answer why questions, not just how questions. So when you flip a light switch tonight, think about what's really happening. Not electrons racing through wires, but an electromagnetic field establishing itself throughout the circuit, pushing all the electrons everywhere at once, delivering energy through space, making atoms in the bulb vibrate so intensely that they glow. That's electricity. That's what's real. That's what Feynman would want you to understand. Not the comfortable lies, not the simplified models, but the actual physics. And here's the beautiful part. Once you understand it, really understand it, everything makes sense. Radio, transformers, generators, motors, circuit breakers, wireless charging, it all fits together. It's all the same physics, electromagnetic fields interacting with charges. That's what education should do. It should take the mysterious and make it comprehensible. It should replace vague words with clear understanding. That's what Feynman spent his life trying to do, and that's what I hope I've done for you today. Now you know what everyone gets wrong about electricity, and more importantly, you know what's right.